cysteine is the next amino acid on the list. You can see it at the bottom here. It is another amino acid with sulfur, so it's a thiol group here. And it's only 1.38% abundance in this table. So I'll go ahead and draw it. Here's your alpha carbon, carboxyl group on the side here, and amine group on the side here. And you'll have carbon kind of separating it from the protein backbone, and then it's just this thiol group of sulfur with the hydrogen on the end here. So it's basically the same as cysteine, except you've replaced your oxygen with a sulfur molecule. And you can see how they drew it here is the alpha carbon and the side chain. So there's only a couple of amino acids with sulfur, and so if you're doing some experiments, you can use this sulfur 35, which is a radioactive isotope with a half-life of 87 days and emitting a high-energy electron. So you can do experiments where you track the sulfur, meaning that you can track proteins and ignore things like DNA, which don't have sulfur. So here's cysteine and the special cases. Oops. You can see the pKa of 8.3, so in a cellular environment it's most likely going to have that hydrogen attached to it because the 7.4 pH will be more acidic than 8.3, and so you'll have more hydrogen ions available to stay attached to the side chain. Selenocysteine is just a variant on cysteine where you've replaced your sulfur with a selenium ion or selenium atom. It has a different pKa, so it has a 5.4 pKa, which means at cellular pH it's more likely to be ionized, where the hydrogen is left and you have a negative charged atom. That's more of a detail. I don't think selenocysteine really comes up much in practice. So cysteine, CYS-C for the abbreviations, has 2 codons. It's conditionally essential, so it's only essential for certain special cases of deficiencies in metabolism or certain infants and elderly. So it's used a lot. It's a useful amino acid. It can help bind to metal ions and various other things. But we did see it with the zinc fingers. The 4 amino acids that help hold the zinc ion in place are 2 histidines and 2 cysteines. So the cysteine would probably be negatively charged in that environment, I would assume. And the histidine would be slightly negative from a polar charge. And so you have some negative amino acids surrounding a +2 zinc ion. And that still has a net positive charge, I think, so it's how it binds to the negatively charged phosphates on the DNA backbone. So another thing that cysteine can do is bind to another cysteine to form a disulfur bridge. So the side chain on one cysteine forms a covalent bond to another cysteine side chain. So if you had another cysteine side chain off to another amino acid, down here somewhere, you would end up with a covalent bond between these two sulfurs, and that's a very strong bond, and that'll hold a protein in shape, preserving that tertiary structure of the protein, just making it less likely to deform. So I already mentioned everything about selenocysteine, just the pKa being different. And just to show here, this is the electronegativity using the Pauling scale. And you can see that sulfur and selenium are very close to the same electronegativity, so they're not going to drastically pull in any electrons compared to carbon and hydrogen, kind of all roughly the same. And then again, you can see oxygen, sulfur, selenium in the same column here, all forming two bonds. And here's a empirically measured atomic radius, and you can see that sulfur and selenium are not too different. So you're not going to have too much of a difference here just based on size or electronegativity. But whatever properties add up to different pKa, that's where the cysteine and selenocysteine will differ. So here's a table of occurrence that you can sort by individual domains of life. And you can see cysteine here is the least abundant in bacteria. Cysteine least abundant in archaea. And second to least in eukaryotes. And third to least in humans. So you can kind of see here cysteine more rare in your prokaryotes and more common in eukaryotes and a little bit more common in humans. So I already mentioned that cysteine can bond to metal ions, and here it mentions heavy metal ions, and it can form the disulfide bridge. And when it does that, they kind of rename this condition as a cysteine, or cystine. I'm assuming it's pronounced different than cysteine. But cystine, I'll just call it that, even though I'm not sure how to pronounce it, is a dimer. It's made up of two amino acids bound together through their side chains. So again, that's going to hold a protein's shape together when that forms. But this is where the name of cysteine came from. Cysteine, as the dimer, was named after the bladder, the Greek word for bladder, kisti, and then that kind of in an English form would be cysteine. Then, just to mention, in the zinc fingers, there's this cysteine, histidine motif or fold. So you have a sequence that's important to have cysteine and histidine in the right spots for it to kind of have a certain function related to the zinc fingers. Just flip through here. I think I covered everything that I wanted to talk about. Yeah, that's everything. I was going to mention that selenocysteine is kind of a special case where you have this UGA, which is normally a stop codon, and there's a process to kind of override that until a specific transcription process that it is supposed to put a selenocysteine in that spot.